Hi, everyone. Thank you for the invitation to present my poster at this year's MTV meeting. Today, I'll be talking about some recent work we've published with the Chandler collaboration out of Virginia Tech, specifically a study of nuclear quenching factors in their detector. To give a brief introduction, when particles interact in a detector, they leave behind energy. And that energy goes into several different channels, the primary ones being scintillation, charge, and heat. But generally, detectors only measure one of these things. And to further complicate matters, exactly how much energy goes into each of these channels depends on the type of particle that left behind the energy and on the detector material. We define a special ratio of the energy left behind in a detectable channel by a nuclear recoil to the same by an electron recoil as a quenching factor. And these are significant because neutrons, neutrinos, and dark matter all leave behind nuclear recoils. So you need to understand what to expect in your detector if you're going to successfully measure these types of particles. So as I mentioned, we worked with Virginia Tech with their Chandler technology from the group of Dr. John Link. And they brought that detector, specifically a small prototype version of it called microchandler, down to tunnel where we can produce monoenergetic neutrons with our tandem accelerator. This is highly mission relevant. Reactors are an intense source of antineutrinos. So being able to measure reactor antineutrinos would allow you to say something about the state of the core of the reactor and detect anything from diversion to criticality. The Chandler detector technology is intended to do just that, sensitively measure neutrinos from a reactor as part of a robust anti-proliferation program. And an important background for them to understand is the effect of fast neutrons in their detector. Because they generally deploy close to a reactor, fast neutrons are a significant background, and they want to make sure they're able to reject those effectively, which is where we come in. So as I mentioned, we used the tunnel tandem Van de Graaff accelerator to produce a pulse beam of deuterons. We directed those deuterons onto a tritiated target, which had, in addition to the tritium, some deuterons from previous experiments embedded in the foil. This produced two neutron populations with distinct energies, DT neutrons and DD neutrons, which means that for every beam energy we recorded data with, we actually produced two quenching factor values, one from DT neutrons, one from DD neutrons. The results were recently published in JINS. You can see a couple of plots here about the experimental setup, some time of flight values from microchandler demonstrating that we're able to isolate these signal populations, and our final results, which are well in line with Burke's theory. If this technology is successful, and we believe it will be, it would be a significant tool for nuclear non-proliferation and for fundamental physics. There's a lot of interesting neutrino physics you can do at a reactor, including searches for a neutrino magnetic moment. As far as the MTV impact, the North Anna reactor has expressed interest in the technology and has allowed deployments there in the past and plans to continue allowing deployments to their reactor facility. And working on this project got us collaborating with John Link out of Virginia Tech, who I'm sure many of you know. This work was published in JINST recently, as I said. You can find the link to that paper in my conclusions section. In the future, we plan to assist Dr. Link's group in upgrading Mini Chandler, which is their slightly larger prototype, with some of the new technologies that were incorporated into microchandler before redeploying it to a reactor as a proof of concept. That will conclude my talk. Thank you again for inviting me to speak today, and I look forward to interacting with you all in the Zoom rooms.